Hello everyone and welcome back. I'm Aditya and I'm back with yet another question on graph. So the question that we are going to solve today is find whether path exists. And just a second, if you are following the playlist, it's isn't it the same question that we solved last time? Yes, indeed it is, and yet I'm back with it. So it's not exactly the same question, it's a variation, and it's a very important variation. I want to share it and show you how it's solved and what are the differences that we face while solving this problem. But yes, by the name, it's exactly the same question, and exactly the same thing needs to be done, but it's different. So let's read the question. Given a grid of size n cross n filled with 0, 1, 2, and 3, check whether there is a path possible from a source to destination. You can traverse up, down, right, and left. The description cells is as follows. A value of cell 1 means it is a source. A value of cell 2 means it is a destination. A value of cell 3 means it's a blank cell. And a value of 0 means it's a wall. So we can obviously by logic traverse through a blank cell because it's blank, and we cannot traverse through a wall because it's a wall. So that is the logic that we need to understand, we need to accept while solving this problem. So here I have been given an example grid of 5 cross 5 size, and the output is false. That is, we cannot reach from source to destination on this grid. So let's focus on the grid. So the grid that is given in the example, you can match what I have just drawn it on a proper grid. And what we are going to do is we are going to try to traverse from source to destination. So what is the source here? The source is 1 that I have marked with green, and the destination is 2 that I have marked with red, and we want to traverse from 1 to 2. So it's given that 0 means that path is unavailable, and because it's a wall, and 3 means we can travel. So clearly we can only go from 1 to 3 because it's a wall, we cannot go here. It's a wall, we cannot go here. It's a wall, we cannot go here. So yes, we are trapped. We can just traverse 1 and 3, and we cannot reach 2. Had this been a 3, we could have easily traversed to the destination. And uh, how do we solve this? And is this a graph question? You might be thinking it feels more like a grid question. But yes, it is a graph question, and that is why I wanted to share this problem. This is a graph question, and it can be solved with breadth first search. I'm just referring breadth first search because I'm more comfortable with it. But of course, we can always use the depth first search for solving this problem as well. So we just need to we need to think of this grid as a graph, and we have to make assumptions for possible edges, possible and valid edges between the grid coordinates, and then we need to just treat it as a graph and do the traversal, either breadth first search or depth first search, and then see if we are able to traverse from source to destination. So yes, we are going to do breadth first search, and we'll see it on the editor how we are going to solve it, because when we are coding you'll be better able to understand and see for yourself how we are going to solve it using assuming this is as a graph. So I'm going to shift to my editor now. So on the editor I've already set up the example that we saw on the whiteboard, and in the function valid path we are going to program our approach. So before we start with the approach, we just need the source and destination. It cannot be none. So to do that, what I'm going to do is I'm going to iterate over the grid. So for I in range n and for j in range n, I'm just iterating over the entire grid, and I'm going to find the coordinates for which the grid I comma j is equal to 1. And if I find that coordinate, I'm going to call it the source because it's the source, right? So I'm going to store source as the coordinates, that is I comma j, as a tuple. And again, I'm going to do grid I comma j equal to 2, that is the destination. When I find that coordinate, I'm going to store it in the destination. So now source and destination are no longer none. They in fact are the coordinates. So now I will start with programming the function. First of all, I'll consider the base condition when source is equal to destination. In that case, I'm simply going to return true because we are already at the destination. Then now I'm going to begin my breadth first search. So you could have done depth first search, but I'll stick with breadth first search. So for that, I need visited equal to set and q equal to a, a list that contains only the source as its element. Now I'll do a loop, and it will loop while the length of q is not equal to 0. As long as q is not empty, I'm going to keep repeating these set of commands. So I'll pop out the first element from the queue and store it in the variable vertex. Then if vertex is in visited, that is if we have already visited over the node, simple breadth search, mind you, so we will just continue. And if it's not the case, we are visiting it now, so let's add it to the visited. We are going to add the vertex to visited. Now I'm going to iterate over the neighbors of this vertex. And on the grid, the what are the neighbors? The neighbors are right, up, left, and down. Right. So I'm just going to make a list. Remember we used to write adjacency, right? For neighbor in adjacency in the graph. But over here, I'm going to create the neighbor, and those will depend on the vertex. So what I'm going to do is I'm adding +1, -1 to the x coordinate, that is left, +1 means right. Okay, the coordinates need to be in tuple, right? So it's all wrong. I'll just remove everything. So the coordinates x comma y are in tuple form, right? So this is now tuple, and vertex 0 will and vertex 1 will give the corresponding x and y coordinates. I'll copy this and paste it 4 times because we have 4 neighbors: left, right, up, and down. Now I'll subtract 1, so that's the left. I'll add 1, that's the right. Subtract 1, that's the down. I'm sorry, up, and +1, that's for down. So we have the 4 neighbors, and while I'm iterating over it, I have to make sure that I'm not getting out of the grid, right? So the grid has some boundaries. So if the neighbor 0 is less than 0, that means we are to left, we are on the left, beyond the left wall of the grid. So if the neighbor 0 or neighbor 1 is less than 0, or if the neighbor 0 is greater, neighbor 1 is greater than n, that is greater than equal to n, or neighbor 0 is greater than equal to n. So these are the cases when we get out of the grid. So when that happens, I just want to continue. I don't want to do anything with it because it's an invalid neighbor. If that's not the case, I'll check if the grid value for for those coordinates. So grid neighbor 0 and neighbor 1, I'll check the corresponding grid value. And if it is equal to 0, that means it's a wall, so I cannot traverse this. So again, I'll just continue. I'll check for other neighbors. This is I cannot do anything with the wall. But again, if this neighbor is equal to destination, that is, if it matches the destination, I want to immediately return true. And lastly, if none of the above is satisfied, I want to check if neighbor is in the visited. So if neighbor is not in the visited, I just want to append it to the queue. So queue.append neighbor. And if during the entire traversal I never meet the destination at the outside of this loop, I just want to simply return false. Now I'll add comment and again make sure that you understand. This case is for the case when we are outside the grid. This is the case where we are hitting the wall. So this is the wall, and this is the case when we meet the destination. And otherwise, we do the simple breadth first search, that is add to queue and do the BFS. So it's a blank, so it's traversable, so we traverse it using the breadth by simply adding to the queue. So it's a blank and not the destination. I'm going to run this program now, and we'll see that it returns false as was expected. So do you remember how we discussed that if it were a 3 on top of the 1, the source, we could have reached the destination? So I'll make that change to our grid over here. I'll remove 0 and add 3 and run the program, and I expect a true. Yes, it gives a true. So that shows that our program is working quite fine. So at the last of this, I want to discuss how this problem is different from, or how the solution was different from our earlier problem, the last problem we solved. So if you're not following following the proper playlist and you haven't seen the last video, you can skip this part. But for those who are following, I want to just take a moment to look back and see how the earlier problem was similar and how, in which ways it is different. So both the problems are exactly the same, just the way of representing the data is different. In the left side, we had a very direct graph question. On the right side, we had a kind of matrix question that we converted to graph for our comfort. So the goal was exactly the same, and I'll bring contrast the two now. So we had to create the adjacency list from the edges that was given as the input, whereas here we created on spot adjacency substitute. We created a list which was nothing dependent on the vertex and was left, right, up and down coordinates of the grid. That is the difference that we had. Other than that, yep, everything was exactly the same. We applied the breadth first search and saw if the traversal was possible. So with that, we are done. Thank you for watching this video.